a DC machine can work as a generator or as a motor. First, let us look at the working of a DC generator. DC generators convert mechanical energy to electrical energy. It works on the principle of electromagnetic induction, that is, when a conductor cuts or links with a magnetic field, an EMF will be produced in it. Now, let us try to understand the working. Let us take a horseshoe magnet having north and south pole. There will be a magnetic field between the poles in the form of magnetic lines of force. Now, take a long conductor and place it in the magnetic field. To measure the electrical activity, let us connect it to a galvanometer. If we move this conductor up and down, we can observe the deflection in the galvanometer. This means EMF is getting generated in the conductor and it is alternating. As we see through the galvanometer, the pointer deflects towards both the sides of zero. Now, if we move this conductor horizontally, there will be no deflection as the conductor is not linking with any flux. It will be moving parallel to the magnetic field. So, we can calculate the EMF with a simple formula, that is E is equal to BLV, where B is the magnetic flux density or number of magnetic lines of force between the poles, L is the length of the conductor, V is the velocity with which the conductor moves up and down. By increasing any one of these factors, we can increase the induced EMF. However, moving this single conductor up and down to produce large EMF is a bit impractical and not efficient. So, we have to rotate it. Because most of the machines like turbines and engines produce the rotational output, it will be easier to convert this action into electrical energy. Now, we have made the conductor rotate. However, the conductor continues to produce an alternating EMF. We know the formula for the EMF generated. When the conductor rotates, another factor gets added to the equation, that is sine theta. So E will be equal to BLV sine theta. Theta is the angle made by the motion of conductor with the plane of flux. We'll learn about the effect of theta later in this video. Now, let us replace the single conductor with two conductor loop ABCD. Portion AB and CD are like individual conductors. If we rotate the single loop conductor between the magnetic field, we'll get an EMF more than what a single conductor could produce. When we look at the rotation, we can understand why it produces an alternating EMF. Let us start with conductor ABCD, which is at 0 degree position with respect to the magnetic field. In this position, the conductors will not link or cut any flux as it will be moving in the horizontal direction or parallel to the flux for a short period. Hence, the EMF and current will be 0. As it rotates clockwise and reaches 90 degree position, it will cut the maximum flux and hence we see the graph showing the positive peak point. Now, let us recall the formula for induced EMF. E is equal to BLV sine theta. We spoke about BLV, but theta was pending, isn't it? As you can see, theta is the angle between the direction of movement of the conductor and the direction of the magnetic flux. For example, at the initial position, conductor AB is moving towards the right and the magnetic flux is also moving towards the right. Hence, there is no difference in angle, so it is 0 degrees. This formula also validates the fact that at 90 degrees, there will be more EMF as the value of sine 90 is 1 and its largest value, the sine component, can reach. Now, as the conductor rotates and reaches the 180 degree mark, it will be parallel to the magnetic flux again. So, we get the current value as 0 and we can see that in the graph too. At this point, the current will reverse its direction. To know the direction of current, we apply Fleming's right hand rule. Let us recall this rule. Stretch your forefinger thumb and second finger perpendicular to each other. If you point the forefinger in the direction of the magnetic field from North Pole to South Pole and thumb in the direction of the motion of the conductor, then second finger will give the direction of current flowing in that conductor. In our case, from 0 degree to 180 degree, the conductor is moving downwards. If we apply the rule to conductor AB and CD, the current will flow in the direction A to B and C to D. After 180 degree mark till 360 degrees, the conductor AB will be moving upwards and CD will be moving downwards. So if we apply the rule again for conductors AB and CD, we get the current in the direction D to C and B to A. So after 180 degree point, the current has reversed its direction. At 270 degree mark, it will cut the maximum flux as it is perpendicular to the flux and the graph reaches the negative peak value. Finally, when it reaches the 360 degree mark, which is same as the initial position, current will be zero. Therefore, as we see in the graph, it is a sinusoidal AC current. But the DC generator is supposed to generate direct current, right? Yes, it will. But every DC generator will produce AC current internally. We need to convert this AC current to DC current. We can do this with the help of a device called commutator. Let us see how this works. We replace the slip rings with the commutator. A commutator is a device with two split rings separated by a layer of mica. It is attached at the end of each armature conductor. Conductor AB is attached to split ring 1, which is connected to brush 1. The conductor CD is attached to split ring 2, which is connected to brush 2. The winding is firmly attached to the commutator, but the brushes are just in contact with commutators. They are not attached and it remains stationary. Now coming to the working of the commutator, in the first half of rotation from 0 degree to 180 degrees, the current will flow in the loop ABCD as we saw earlier. The direction remains the same in the outer circuit also. Now observe the commutator brush pair. Split ring 1 is connected to brush 1 and split ring 2 is connected to brush 2. In the second half, from 180 degree to 360 degree mark, the current direction will be in the loop DCBA, opposite to that in the first half. If the commutator was not there, then the direction of the current in the outer circuit would reverse its direction. So, when the current flows in DCBA, the conductor CD is connected to split ring 2, but now it is in contact with brush 1. Similarly, AB connected to split ring 1 will be in contact with brush 2. So, in the outer circuit, the current direction will be the same for both halves of rotation. This is how we convert AC to DC in a generator. When we look at the graph, it will be unidirectional current, but it will be actually pulsating. This current cannot be used. We need a linear current without pulsation. So to make it linear, we need to add a few more conductor loops. Let us add one more loop and two more split rings. Now, the graph is a bit smoother. In the actual DC generator, there will be many such conductor loops. To hold these conductors in a place, we use armature conductors and will replace the permanent magnets with electromagnet. So that is about the working principle of DC generator. To sum up, we learned about the generation of EMF in a single conductor, single loop generator, the formula of generated EMF, current direction without a commutator, and AC to DC through commutator. In the next video, we'll learn about the types of armature windings placed in the armature slots. See you there.